Gabriel Spadon, who has a PhD and a master's in computer science from the University of São Paulo. Gabriel has joined Dalhousie University and as a postdoctoral fellow and is currently co-hosted by IMT Atlantique in France. He is studying neural-inspired models, graph-based deep learning, and complex network dynamics applied to transdisciplinary topics such as human behavior and ocean and environmental monitoring and protection. Gabriel, please, you can get started.
Thank you. Can you see my screen?
Yes.
So good afternoon, everyone. As Fabio mentioned, I'm Gabriel Spadon. I will be talking a little bit about vessel signature detection. This is a knowledge base and a data fusion approach. So for this presentation, I will be talking about the data set Mark was just also presenting some results. This data set is the Environmental Study Research Fund data set, also known as the ESRF data set. This is a data set we got our hands from JASCO. This is a passive acoustic monitoring data set. We have 20 stations spread all over Atlantic coast Canada. The collection of this data ranges from 2015 to 2017, save some exceptions. The data set was all collected on a duty cycle of 20 minutes with 11 minutes of 8 kilohertz files and 1 minute of 150 kilohertz files and 8 minutes of silence. So the total size of this data set is around 42 terabytes. But when we concern vessel signature, the 11-minute audio files are the target ones to choose. And working just with those, this data set size drops by half, so around 20 terabytes of size. So this data set is unlabeled. As Mark Thomas mentioned, we don't have labels for vessels here, although lots of publication was research and publications were done on other topics in the same data set. So given this open flank for research and vessel signature detection, we joined this data set with AIS data set that we had from Aspire, former ExecEarth, that has a bounding box that covers all the hydrophone that we have in this region. And with that information from AIS extracted both from satellites and terrestrial antennas, the idea is to merge the two data sets in a sense that for the audio file duration, we know whether if there was a vessel or there was a vessel in that region or multiple vessels and their distance from the hydrophone or their closest point of approach in this case. So what we do is that we leverage a technique, a tool set from Meridian called AISDB, which stands for Automatic Identification System Database. AISDB is a tool that is developed in Python and Rust. As the name says, it's a SQL database where we can query AIS tracks both in space and time. But besides that, it has lots of tool sets for working and preparing AIS data for research. This is the case for position cleaning, trajectory modeling, streaming and decoding of AIS messages, raw AIS messages. Also, integration with open source datasets, such as the one that give us information about the bathymetry during the vessel voyage and the distance from shore to port, besides geometry, MEMS duplication, interpolation, and other techniques. So once we have the data, the acoustic data, the AIS data, and the tool, the purpose of everything here is to make this useful. So turn these labels into, turn these AIS messages into labels so we can allow further research on this front to be done. So what we do is that for each one of these stations, we consider a radius of 100 kilometers. And from 100 kilometers to 1 kilometer, we will check the presence of vessels using AISDB for the exact duration of the audio file from the ESRF dataset. So given a station, we will first query and check if there is any vessel during the audio file 100 kilometers away from the hydrophone. If no, this means that we assume that there is no vessel in the audio file. But if there is a vessel, then we query the inner distances from these radios up to the closest point of approach. So the point where the vessel was the closest to the hydrophone. We do that not only for the audio file duration itself, so for being sure that we are capturing different vessels that might not have transmitted in the duration of the audio file, we have an offset of 4 minutes before the audio file and 4 minutes after the audio file that will result in a 19 minutes of duration. So this gives us around 19 different AIS messages linearly interpolated at that time. And during this span of AIS messages and audio file is where we do the merging between the two data sets, allowing us to further work on the vessel detection analysis here. And I'm using station 15. It's the main station that I will be using to show some of preliminary results here. Once we have the data labeled, the process goes very straightforward. So the problem is, as already mentioned in previous presentation, is to match a spectrogram with a label. In this case, I'm working with presence and absence of vessels. And I'm working on this more simpler case because my goal is to optimize the training process given the amount of data that we have. So how we change the training process without incurring in more extensive and complex models and still achieve better performance on the detections that we are doing here. So each audio file will be sliced for 3 seconds with 1 second of overlap. These segments that we slice, they will go through a low and high pass filters where we will fit the spectrograms in 10 to 1,000 hertz frequency. And the spectrogram that I'm using here is just a simple power spectrogram in the decibel scale, which before going through the network goes through a single channel normalization and a grayscale and becomes a grayscale image. So just for an idea of numbers, station 15, which is the one that I'm using for experiments, has around 1 terabyte of audio files. From all audio files that we have from that station, around 60,000 audio files have vessel presence in it. When we convert that to useful machine learning data, that becomes around 1,200 different spectrograms per audio file, giving us 15 millions of spectrograms at the end of the whole process of this station, where 7 million of that is from positive vessel presence and 7 million for the absence of vessels. So once we have that information, the process goes towards working with the model. And as I mentioned, I'm working with very simple techniques. So the power spectrogram and the ResNet. The ResNet is kind of a to-go choice when we are working with CNNs, and computer vision is a very traditional technique, almost canonical for that. It has just 4 blocks of layers, and it's very well known by the skip connections. So far in the past, when we were training neural networks and working with gradient descent to do that, it's very common to go towards a problem called vanishing gradients. And ResNet just overcome that by allowing these skip connections to move forward some of data that was shared in the past. So in a way that we could restore these gradients and allow the network to train and to train in a feasible time as well. So that's why I'm working with ResNet for these reasons. And once we have the model, we have the data, we have the labels and everything else, then we go to the optimization strategy. And here is where things start getting a little bit more confusing. Traditional neural networks, they are trained on a usually constant learning rate or a decaying learning rate to achieve better results. But the problem here is that we have a lot of data. So that's what everyone in deep learning wants. So you have a lot of data and you have a lot of labels, and how you make that work, how you make that feasible without having a tremendous amount of power, computer power to do that. So if we just train the network in the way that it should be trained, traditionally speaking, we too closely move towards overfitting, because the data is so large and the network tends to focus in the first data distribution that it will be seeing the first steps of the training. The cosine annealing, which is what I'm using here, it's what makes the difference, because the cosine annealing, it's kind of a cyclical learning rate scheduler, which has different parameters than a cyclical learning rate, but it does allow us to do these ups and downs as we are showing different data to the model. And as we are showing different data to the model, we not only tweak the learning rate, but we learn the model from one stage to the other stage, where each stage is given by these valleys in the image here, in the cosine annealing image. So each model here highlighted is one model that is trained, one slice of the data that we have, that later will be transfer learned and keep learning until all the data in the whole station is done. And how that differs from traditional machine learning. So machine learning, usually we do gradient descent, single batch gradient descent, or mini batch gradient descent, when we divide the image and we divide the data, and then we average the results. What I'm doing, it's kind of a third step, where we have a micro epoch. So every iteration of the learning rate scheduler, we train a different model. We train a different network, and each network works separately, but inputs the other network. And that's what allows us to cover more ground in this landscape here, where this landscape represents a simplification of our problem, where all parameters are in terms of shapes, and we are looking for the position which is the lowest one, as the whole problem is an optimization problem. So just for the sake of time, I will go for the results. And the results for doing a different way of training, focused on this data set and the data we have, allow us to achieve more performance without the trade-off of having more computational power or computational needs to achieve these results. So traditionally, training the network with a ResNet 18 and also a power spectrogram, we usually achieve a 65% of true positives in the identification of vessels up to 100 kilometers of distance, where closer to the hydrophone, this is much higher, but farther away in larger distance, this gets harder. But our model that we are achieving with these changes in the training has actually an opposite behavior, where we achieve 77% of true negatives, which are the background sounds, and 85% of true positives, which are vessel presence. which means that by just tweaking heuristically the learning process of the network, we can cover more ground with more data and find a distribution of the data that generalizes well for a large data set, allowing us to achieve better results with even simpler techniques and models. So just final remarks, the contributions that I'm looking for here, it's a terabyte label data set and a training pipeline that works with this data set, so that makes feasible to work with that amount of data and extract meaningful information from that. Of course, there is a trade-off. If you use larger and deeper networks, the performance increases. You might not need to change the way that you train your network, but the combination of these two things, more deeper networks and different ways of training network, also have the potential to increase even more this performance. And for the year of 2023, this data set will be submitted for publication, hopefully for scientific data, where we expect to share all 20 terabytes of label data. Not sure if it will be 20 terabytes. The idea is to compress this data a little bit without losing information. So I'm working on that. So how to share this data without losing the performance that I'm showing to you. And so for 2023, the idea is to have that, the data set and the techniques, training pipelines, everything else that make feasible the detection of vessel, classification of vessels, and also location, possibly the location of vessels as well. That's all for me today. Thank you very much. I will be glad to take any of your questions.